Right, let me start by reminding everybody what the model of quantum computation was. In fact, I didn't finish because I started doing what the state of a quantum computer looked like. So we started with the set 1 to the n of classical states. So a state of a classical computer, it's got n bits. Each bit must be 0 or 1. That's all there is to it. I also talked about a probabilistic computer. If you don't actually know what random decisions you've taken, then a good way of representing the state, as far as you know, is as a convex combination of classical states and the coefficients associated with each state to give you a probability that you're in that state. And then a quantum computation replaced an L1 combination, or a positive L1 combination of classical states with an L2 combination with coefficients in the complex numbers. To be more precise, what I actually wrote, or this is a lie, what I initially, or what I wrote after somebody pointed out that I made a mistake, a typical state of a quantum computer looks something like this. Divided by a normalizing factor, which, of course, has to be that, but I forgot the square root when I said that at the end of last time. So it's normalized so that this vector has norm 1 in L2. Well, the particular space we're talking about, I suppose we can write L2, and that's your ground set, and that's where the coefficients lie. Let's have a few examples of... Before I give examples, I now want to say, anybody who's seen a little bit of quantum computation will probably really dislike what I've just written there. Because I'm not using the standard notation of quantum computation. Well, I am going to use the standard bit. So I'm now going to change from something that people who know all about quantum computation will dislike, but pure mathematicians will find sort of reasonably nice, to something that quantum computing people will like, and pure mathematicians, at least initially, will dislike intensely, I think. And that is, instead of writing V epsilon, I'll just write epsilon. And if you know a slight bit about quantum mechanics, that's a ket. And a bra is one of these sorts of things. And if you put them together, you get that. Now, what is all this notation? We don't need it very much. If I've got some... We're taking formal linear combinations of things here. So I take some states of a computer, and I want to take formal linear combinations of them. So to turn those states into vectors that I can attach coefficients to, I just do that to it. So epsilon is the sequence of noughts and ones that you might have. To turn that into a vector, I write something like this. But if I want, supposing I want to turn something into a dual, an element of the dual of the Hilbert space. So people like not to identify a Hilbert space with its dual, because that's somehow not a natural identification or something like that. So if you want to think of something as a linear functional on a Hilbert space rather than a vector in the Hilbert space, you do it that way around. And then if you want the inner product of two vectors, or two states, you can just put them together, and that's the inner product of x with y. We won't be really doing that very much. We'll just be using, on the whole, we'll just be talking about vectors and not worrying about inner products. But one of the things that people like about this notation is that you can, for example, represent a rank 1 operator by doing things like something like this. And if you want to know how that operates on Z, you take your Z. This is what does this rank 1 operator do to Z? You just stick it in front of Z. And then you get the inner product of y and z multiplied by x. And pure mathematicians have a different notation for this. They might say something like, for this, they might say, this is the operator x tensor y star, and the next tensor y star applied to z gives you y star of z times x. It's just a different notation for the same sort of thing. But as I say, that's just a little remark to explain why this notation isn't totally crazy. But we'll be using it. I think there's a normal process that pure mathematicians have to go through, which starts off with hatred, and then it becomes a kind of resigned acceptance, and then ends up with something sort of possibly a little grudging affection or something. I've sort of got to about halfway between resigned acceptance and grudging affection for myself, but I wish you luck in getting into that process. So, if you just look at, what about, we had bits before, each, to n bits, each bit could be 0 or 1. And now we're going to have things called qubits. I don't know whether you can really give a formal definition of qubit. I just think of a qubit as a bit when I'm talking about quantum computation. So let's write down some states. Suppose you've just got one qubit, then what will a state look like? Well, the qubit can take value 0 or 1, and so a typical state would be of the form alpha 0 beta 1 with alpha squared plus beta squared equals 1. But if I've got a quantum computer with 2 qubits, then what can the possible states be? Well, we have the basic states, there'll be things like 0, 0, 0, 1, 1, 0, and 1, 1. And so now, a state of a 2-qubit quantum computer will be something of the form alpha plus beta. Now plus delta with again the sum of the squares equaling 1. And in general, I could rewrite this thing up here as a typical state being of the form sigma lambda epsilon epsilon with sigma lambda epsilon squared equals 1. Now, you could just say this is a Hilbert space where the of dimension 2 to the n, where, because 2 to the n's a power of 2, it's somehow natural to index the basis vectors with binary sequences of length n. But actually, there's slightly more to it than that, because the set 0, 1 to the n can be given all sorts of structures. And in fact, a good way of thinking about this space here is it's a tensor product of n two-dimensional copies of little L2. Just to make that reasonably explicit, if there are people who are totally happy with tensor products, let's look at this two-dimensional case. I want to see how we can think of this as just a different notation for the tensor product of two-dimensional vector spaces. So let's say that the first vector space has a basis, and I'm going to call the vectors in that basis 0, 1, and 1, 1. So those, I've just put this little subscript 1 to say that's the first vector space that I happen to be talking about. And so I've got these funny names for the vectors in the first little L2. Then I've got 0, 2, and 1, 2. And if I take a tensor product of these, a basis will take the form, well, it'll be all things. I'll just write down the basis elements. Those four vectors there will form a basis of the tensor product of the vector space that had this as its basis vectors, and the vector space that had this as its vector basis, as its basis vectors. Again, try not to think of naught as sort of taking a value. This is just a name of a vector. And after a while, we could say, let's not bother with a tensor product notation. Let's just write it like this. Instead of, let's do this one. Instead of writing it as naught, tensor 1, 2, we'll just write it like this. Naught, 1, 1, 2. I'll just stick them next to each other, and the convention is if I do that, it's a tensor product. The next stage of the process, I could say, well, instead of writing as 1 and 2, I mean, I'll just always put the 1, 1 over there and put the 2, 1 there, so I might as well just write it like this. And then the next step is, well, I really need to write that. So actually sometimes all these things are useful. So I will have, I don't know whether I'll use all 4, but I in principle have 4 interchangeable pieces of notation that all mean the same thing. I've got this, 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 and this. So here is, for example, a way of writing a state, just one particular state. Let's consider the state 1 over 2 to the n over 2 sum over all epsilon. First of all, let's just check that that's a valid state. And it is, because the sum of the coefficients, the sum of the squares of the coefficients is 2 to the n times 1 over 2 to the n, which gives us 1, and this ranges over, because this ranges over all 0, 1 strings of length n. But we could also write this as, we can decompose this as what have I done here? I've put the first qubit into a superposition of 0 and 1. And I've done that for all the qubits. Why is that the same thing? Because this is just this tensor product thing. So a typical term here will take a 0 or a 1 out of each bracket, product them all together to get something like, if I use that notation, and divide by 2 to the n over 2. So it's just another way of writing things. And as we'll see later on, being able to think of the state as a tensor product of states is a very nice thing to do. However, if you know anything about tensor products, you know that there's a sort of old undergraduate trap to fall into, to think that every element of the tensor product V tensor W must have the form little v tensor little w for some V in capital V and W in capital W, and that's far from true. A general element has to be a linear combination of such things. And of course exactly the same happens in quantum computation, because it is a tensor product. So what I've written here, which is happens to be of the form a state concerning the first qubit tensor, a state concerning the second qubit, all the way up to the last one, is a very, very special form of a state. And this is, we could call this a separable state. This is an example of a separable state. So a separable state would be anything of the form, let's write it in tensor notation, so the big product over all I of alpha I naught, so I equals 1 to n alpha I naught plus beta I 1, where we've always got alpha I squared plus beta I squared equals 1. So those are very, very special forms of state. If those were the only states that you could get in a quantum computer, you could simulate your quantum computer with a classical computer quite easily. That's been proved. And it's a sort of exercise, really. So the whole power of quantum computation comes from the fact that not all states are separable in this way. And a state that's not separable is called entangled. Now let me give you the simplest entangled state, or one of the simplest entangled states. And to do it, I will just go back to tensor product of two vector spaces. What's the easiest way of producing something that's not of this form? You just take a basis, say you've got a basis here, E1, E2, and a basis F1, F2. So let me take E1 tensor F1 plus E2 tensor F2, and you just can't write that as a product of one thing, product of another. So the exact corresponding example here would be something like that. That would be a good example of an entangled state. This particular state, I'm sure the notation was a little bit different, but it underlies, you may have heard of the Epr paradox, Einstein-Podolsky-Rosen. The idea is, let's just think what would happen if we did a measurement. Perhaps I'll remind you what happens with a measurement. Supposing I measure a qubit, so what I do is I run my quantum computation in some funny superposition. I then actually look at the ith bit, let's say ith1. I'll look at the first bit. Then that's always going to give me some deterministic value. It'll either, if it's a physical thing, I'll look at it, it'll either be a 1 or a 0. When I look at it, it's not going to say I'm 1 over root 2, 1, plus 1 over root 2, 0. It has to be one or the other. So what happens to the rest of the state after you've done that measurement, after you've looked at the first bit? Well, it just does the most natural thing it could possibly do. It sort of projects onto the subspace of L2, of this Hilbert space that's consistent with your observation. In other words, it takes, I've lost it now, I want the version with, it takes this sigma lambda epsilon, and then maps to, I wrote this last time actually, so it maps to sigma over all epsilon such that epsilon 1, if I've got a 1, epsilon 1 equals 1, lambda epsilon divided by the sum epsilon 1 equals 1, lambda epsilon squared to the half. So you say, you send all the bits that are inconsistent with this observation to 0, and so maybe project is not quite right, but all the ones that are inconsistent to 0, and then you normalize the rest, so it goes back to having L2 norm equal to 1. And the probability that you'll get 1 is this. So over here, supposing we take a measurement of the first qubit, then what's the probability that we'll get 0? Just before I say that, I've got to tell you the story of the supervision that I gave recently, because it's somehow strangely relevant to this. So one of my supervisees came along, and there was a question about Rouché's theorem finding zeros in various quadrants of the half plane. And she came up with you were supposed to prove that there's exactly 1 0 in all 4 quadrants of the complex plane. And her argument went like this. There are 2 zeros in the right half plane, and 2 zeros in the left half plane. There are also 2 zeros in the upper half plane, and 2 zeros in the lower half plane. Done. And so I hope you can, well, this sort of almost, the form of this tells you the counterexample. So I drew you a picture like that, and she said, oh yes. And here, what is the probability that we will measure a naught if we measure the first qubit? Well, what have we got? Let's just write the vector like this. We've got a 1 over root 2 there, and 1 over root 2 there. If we take a measurement, then we're measuring the first qubit, so that's the sort of x-coordinate. So I want to know, am I in this half, or am I in this half? So to work out the probability I'm in this half, I just add the squares of all the coefficients, so I get a half. So there's a 50-50 chance that I'll be in the left half, and a 50-50 chance I'll be in the right half. So with a 50% chance I'll get the left half, 50% chance I'll get the right half. If I get the left half, it'll collapse to something that's just what it was, proportional to what it was. It's a 0 on the right-hand side and proportional to what it was on the left-hand side, which means it must be 1, 0, 0, 0. And if I'd got the right half, in other words, if the first qubit had measured 1, then it would have become 0, 0, 0, 1. It would have picked out the right half and normalized to make it have norm 1. That's what a measurement does. Now I suppose I do a second measurement, this time of the y-coordinate, or the second qubit. Well, if the first qubit, when I measured it, gave me a naught, then I'm over here. So when I measure the second qubit, I'm now completely stuck in the bottom half plane, so it's guaranteed to give me a 1. If the first measurement gave a 1, then that sort of collapses things, so the second measurement is now guaranteed to be 1. And similarly, if the first measurement, so that was a 0, sorry. If the first measurement had been 0, the second one is guaranteed to be 0. If the first measurement is a 1, then the second measurement is guaranteed to be a 1. And what's the Epr paradox? Well, the Epr paradox is you take this state, and then you send the first qubit off to someone called Alice, traditionally, and then you send the second qubit off to Bob, also traditionally, and Alice and Bob live such a long way apart that it takes speed of light. It takes light a noticeable amount of time to get from Alice to Bob. Then Alice makes a measurement, and they've sort of decided in advance at what time they will take their measurements. So Alice says, I'll make a measurement. Actually, I don't know whether and then quite makes sense if they're separated. Whatever we do, Alice and Bob make measurements sufficiently like that, but there's no signal can pass from Alice to Bob before Bob makes his measurement. Nevertheless, the prediction of quantum mechanics will be that, for this simple reason, that whatever measurement Alice makes, Bob will make the same measurement. And, well, people didn't like that, or Einstein didn't like that, because that suggested if quantum mechanics was genuinely probabilistic, then somehow making the measurement should be causing something to happen. But if the same thing has to happen to Bob, that suggests that some signal has had to pass from Alice to Bob faster than the speed of light. And there are developed to this Bell's paradox and things. There are two very natural principles that one might want to hold on to. One is locality, which just says you can't pass signals faster than the speed of light, and the other is, I think generally known as realism, that says there must be some reality about what's going on underneath before you make the measurement. And those two, it turns out, with little simple phenomena like this, you can actually show that they can't both be true. Anyway, it may be puzzling from a philosophical point of view, but just from a pure mathematical point of view, there's nothing particularly difficult about this state or what happens when you measure it. It's just quite what happens in the real world is a little bit, has puzzled people and people are looking about it. Very thanks. But we can forget about all that. And there's a lot of quantum mechanics that we can forget about. We can also forget about measurements being eigenvalues of emission operators and things like that. We don't have to worry about that. We just do what I've done. We say, I'll take half the cube, look at the total sum of the squares, and that's gives me the probability that I get that half, and then I make that lot 0, and I'm in this half, and I normalise. That's all that a measurement is from our point of view. Now, I've not said the most important thing about quantum computation. How do you actually compute things? It's one thing to have a computer that's in a state, but how do you change the state of a computer? Well, in classical computation, what you do is, obviously it's particularly the reversible thing that I talked about last time. We were thinking of an operation as being some function or a bijection from 0,1 to the n, 0,1 to the n. But obviously we don't just take any old bijection from 0,1 to the n to 0,1 to the n, otherwise you could just say, I'll take a bijection that does the entire computation for me all in one step or something like that. The whole point about computers is that what they're good at is very, very simple. It's doing over and over again lots of very, very simple things. And by simple, the normal meaning would be just things that you can do to about 2 bits at a time or something like that. You focus your attention on 2 bits, you do some operation depending on what those 2 bits are, and then you move on to some other bits, and so on. So a classical computation has to be a composition of a large number of very simple operations that apply just to a small number of bits. And the same principle applies to quantum computation, but what is the quantum analogue of bijections from 0,1 to n to 0,1 to n? Well, we take our Hilbert space, and we've got vectors of norm 1. We want to send vectors of norm 1 to vectors of norm 1. And there is a class of functions that is well known to do that, and that's the unitary maps. So the basic operations of a quantum computation are simple unitary operations, unitary maps. And rather than say precisely what a simple unitary map is, I'm just going to give a few examples. Let's begin with a very simple one. We'll take a NOT gate. So I fix on a qubit, and I just want to change it from 0 to 1 or 1 to 0. That way of talking makes it sound just like a classical computation. But what I'm doing there is telling you what I do to an element of the basis. So if I happen to have that basis element, and I'm doing a NOT gate on the first qubit, then that will map to 1, 0, 0. And if I have, say, 1, 0, 1, that will map to 0, 0, 1, and so on. And moreover, if I had, say, alpha times that plus beta times that, it would go to alpha times this plus beta times this. So in order to say what a quantum operation does, I can say what it does to one of these classical basis states and then extend linearly. So naught plus something or other to 1 times that. I'm actually going to talk a little bit more about single qubit operations. You might think at first, before you thought about it properly, but that's about all you can say for single qubit operations. But that's very much not the case, because we aren't doing classical reversible computations, we're doing quantum ones. So if it was just classical, then the only ones would be the identity and flipping the 2 rounds. I've just got 2 possibilities for the first qubit. But in the quantum world, I can get anything in between. So let me just show you how to... This is, it looks quite like this. It's the square root of naught. Not the unique square root of naught, but I'll do naught maps to 1 over root 2. Naught plus 1. And 1 maps to 1 over root 2. Naught minus 1. Well, let's represent that as a matrix. It's much nicer. So, well, what is the matrix of that? It's just 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2. And I hope that squares to, if it doesn't. It's the square of that, which wasn't the square root of naught actually after all. But we could have got the square root of naught by probably putting a minus over here or something. What does that square to? Give me 1, 0, 0, minus 1. Yeah, it's not quite such an interesting thing. Now, now what does 1, 0, 0, minus 1 do? Well, it just takes. Is that right? Or is it just the identity? It's the identity. Okay, that's rather disappointing. Okay, but I could have got the square root of 0, but actually this is the one I want to talk about because I leave it as an exercise to get the square root of the NOT gate. This has got a different, this is called a Hadamard gate. And Hadamard gates are rather useful things. Here's a reason that they're quite useful. In a quantum computation, you sometimes want to get very, very rapidly from a computational basis state to a state that's sort of evenly spread around all possible computational basis states. So you might want to get very, very rapidly from this state to 1 over 2 to the n over 2 sum over all epsilon. Now, how can you do that? Well, what does this do to the first qubit? It replaces it by 1 over root, well, it's over here, replaces it by 1 over square root 2 0 plus 1. So if I compose some Hadamard gates, one for every single qubit, then if I start with 0, 0, 0, which I will now think of as the product like that, then applying a Hadamard gate in turn to each qubit converts each one of those into one of those, so I get 1 over 2 to the n over 2 times, well, I get this thing that I wrote over here. And that is exactly spread things evenly out over all the qubits. If I'd started off with a different computational basis state, I would have got some minus signs around the place here as well. And I would have got another state. So I'd have some plus or minuses here. What would happen if we measured? What would be the probability? Supposing I measured each qubit in turn and thereby collapsed the whole thing down to a single point of the qubit. What's the probability that I would get a particular epsilon? The answer would be 1 over 2 to the n. And that's the case whatever the signs. So does that mean, I just want to draw attention here to the fact that if you measure everything, you somehow get the same result, and yet these are extremely different states because you've got very different phases. And how does the difference show up? The difference shows up because you can apply unitary maps, such as the inverse of this, and if you do that, then you can bring everything back up just to a simple computational basis state, which will depend very much on the phases that you had here. If you had just a completely random collection of signs, you won't be able to do that, but if you've got very special ones that arise from these Hadamard gates, then you can collapse it back up again. And that's actually what's so good about quantum computation. It gives you this possibility of taking a simple computational basis state, sort of spreading it around, doing some stuff to it, and then unspreading it, and getting an answer that depends on some property of what you started with. I'll say a lot more about that, but I'll just mention now, so you can bear it in mind, the thing that really distinguishes between quantum computation and probabilistic computation. And that is that when you apply a unitary map, you can, well, we've already seen actually that this, when squared, gives me the identity. So if I start with 0, I apply a Hadamard gate once, I get this. If I apply a Hadamard gate a second time, I get back to 0 again, which means that something that was sort of spread out managed to get put back together again. And that depended crucially on cancellation. When you apply the Hadamard gate again to this, you get a half 0 plus 1 plus a half 0 minus 1, and the two 1 bits cancel out. By contrast, if you've got a probabilistic computation, as soon as you've started spreading things out and introduce a bit of uncertainty, if it's reversible, in other words, if it's a bijection that you're applying, you're just probabilistically choosing what the bijection is, there's no way of getting it back. A convex combination of genuine convex combinations that haven't got just one in one place and 0 everywhere else can't get you back to something that is 1 in one place and 0 everywhere else. So that's the really enormous difference between quantum computation and probabilistic computation. One other type of gate that I would like to mention now was a rather general phenomenon. It's called a controlled gate. So supposing you've already got a gate that does one thing. So supposing I've got some gate that applies a function to a couple of qubits here, and I want some kind of if-then step. I want to say if one thing happens, then I'll do one operation, and if that thing doesn't happen, I won't do that operation. Then I can take another qubit here, and I can just say, if that qubit is 1, I'll do the operation, which was a bijection, and if it's 0, then I won't do it. Let's just think of it in the 3-bit case. Supposing I've got an operation that I can do to pairs of qubits, and I introduce a third qubit. So now my space, or my computational basis, is functions on a 3-dimensional cube. Supposing I want to use the first bit, i.e. the x direction, as the control. So I want to say, I'll do the yz operation, but only if x is 1. Well, what that's saying is, when x is 0, I just leave this lot alone. So if I started with alpha, beta, gamma, delta here, it will remain alpha, beta, gamma, delta. But over here, I'll apply the unitary map that I had before. That clearly is still a unitary map. It's just got a matrix and looks like this, 1, 1, 1, 1. And then the unitary map that I used for the 2-bit thing in the other half. And controlled gates are extremely useful in quantum computations, and we'll be using them. That's why I wanted to mention them. And also I should mention that all the reversible computation things that we talked about you can do in a quantum computation, because those are just given by permutation matrices. And those are obviously unitary. So if I take, what's a reversible computation? So I take 3 bits. Actually, I just want to give you a little, maybe slightly more of a view of what's going on. By just thinking what the matrix of a simple unitary map looks like. So supposing my operation is something that's applied to the first 2 bits, 2 qubits. Then you might think, oh right, we're talking about well, the 2 bits can have states 0, 0, 0, 1, 1, 0, 1, 1. So you might think we're talking about a 4x4 unitary matrix. The answer is yes, we sort of are, but that 4x4 matrix is tensored with a whole lot of other stuff. So supposing I do some operation, let's just imagine that I've got n qubits, and I do a Hadamard gate just on, well, that's just 1 qubit. Okay, well, let's do a Hadamard gate just on the first qubit. Why not? So what's its matrix going to look like? Well, if I write the basis out in this order, 0, 0, 0, 0, 0, 0, 0, 1, then I'll get to here, and I'll have 1, 0, 0, 0, 1, 0, 0, 1, and so on. So I've got some big square matrix. The Hadamard gate will say that 0, 0 goes to some superposition of 0, 0, 0 with 1, 0. So we'll get, let's put a 1 over root 2 out here. I'll get 1, 1, 1, minus 1. And then this one's going to be paired off with this one. So I get 1, 1, 1, minus 1. And in general, all going to end up with identity, 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 minus identity. That's 1 over the square root of 2. And similarly, if I've got a 2-qubit operation, then typically, and if it applies just to the first 2 qubits, then it's going to be some 4x4 unitary matrix tensor with the identity. So you take your unitary matrix, whatever it is, and then you just put identities by every single coefficient to get some 2 to the n by 2 to the n matrix from your 2x2 matrix. Okay, I mean that's just saying what it means to tensor a linear map or another linear map and what happens to the matrix. But nevertheless, I don't know, it's somehow helpful to think about these things in various different ways. I think I'm now going to stop talking about quantum computation for a bit and talk a little bit about the problem of factorizing, because at the moment it's not clear why quantum computation would be good for this particular problem of factorizing. So I'm going in 2 directions. One is, let's see what quantum computation can do for us, and the other is, we want to factorize. It would be enough to do blah, 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 it would be enough to do blah, 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 and we hope that at some stage we meet in the middle and say, wow, with a quantum computation we can actually factorize. And I'm just going to jump from one to the other. So first I'll be doing the forwards direction now, but in order to give a bit more motivation, and I want to start doing things backwards. I won't have time to do all that much in this lecture, but I want to reduce the problem of factorizing to problems that are more amenable to things that can be done with a quantum computer. I might as well give the game away slightly. It turns out that the real thing that quantum computers are very, very good at, and I've given a slight hint of this in my remarks already, is doing Fourier transforms, discrete Fourier transforms. So Fourier transforms are a classic instance where you do a Fourier transform, it takes something that's very, very pointy, this is sort of the uncertainty principle, and spreads it all over the place. And the inverse Fourier transform will take something that's spread all over the place, if it arose from something that was very pointy, which is not all the case, usually isn't the case, but if it is the case, and can make it pointy again. And that's going to be extremely useful to us. So the aim here is going to be to try to get from the problem of how to factorize to some problem that we can solve if we've got a quantum computer that will allow us to do super fast Fourier transforms. You might say, actually, isn't there something called the fast Fourier transform? Yes, there is. That takes time n log n. However, we're talking about an exponential dimensional space here, and n log n just ain't good enough if n is already exponentially large. So these Fourier transforms are going to be, well, faster than ought to be possible. I'll have some remarks about that. I mean, sort of, we're roughly speaking saying we can take a Fourier transform in log n steps, which doesn't sort of necessarily sound very plausible. But one has to qualify all that statement. In the textbook by Nielsen and Schwank, I happen to have here, I might as well show it to you. Recommended book. It's recommended if you want to become extremely knowledgeable about quantum computation. It's not absolutely recommended if you're trying to find the minimal route to understanding Shor's algorithm, which doesn't get done until page 200 and something. But a lot of you just have to work out what you need to read up to that point. But it's a nicely written book. And a pretty standard book, I would say, by now. Yeah, so you might think if you can do incredibly fast Fourier transforms with a quantum computer, why aren't people getting terribly excited? Why doesn't that mean you could do massively fast multiplications, for example? And the answer is, it's all to do with the measurement. You can do a very fast Fourier transform, but then it's just sort of spread out all over this, it's a superposition of states, and you can't actually sort of get your hands on this entire function. You can just do little measurements of it. So finding ways of using this super fast quantum computation is a non-trivial business. Right, so let's just do the first reduction. So we've got a number n, and we'd like to factorize it. So the first thing is going to be the observation that if you can find a non-trivial square root of 1 mod n, then you can factorize n. Well, let's first say what a non-trivial square root of 1 mod n is. Take n equals 15, say, a favourite composite number. Then can you find a square root of 1 that's not plus or minus 1 mod 15? As an exercise? Yes, indeed. And so let's suppose we've got a square root of, just to convince you that there is such a thing as a non-trivial square root of 1. At least for one example. I'll talk about that in just a moment. But let's suppose we've got one. Supposing x squared is congruent to 1 mod n, then you do the only thing that's reasonable to do. You know that x minus 1 times x plus 1 is congruent to 0. In other words, x minus 1 times x plus 1 is a multiple of n. Now, if n divides x minus 1 times x plus 1, then it's got to have a common factor with x minus 1 or a common factor with x plus 1. And if n has got a common factor with some number m, some non-trivial common factor, notice that x plus 1 and x minus 1 are less than m, so this is not going to be, well, there's one thing that could go wrong, but we'll come to that in a minute. Well, no, let's come to it now. The thing that could go wrong is if we have got a trivial square root of 1, in which case x minus 1 might be 0, or x plus 1 might be 0 mod n, in which case we don't get anything at all. But if we've got a non-trivial square root of 1 that's not plus or minus 1, then we've got some n with a non-trivial factor in common with n, and then we can, then we're in business because we just apply Euclid's algorithm, which is a very, very efficient thing to do, find the highest common factor of these two, and you've got a non-trivial factor of n, and then you reduct. If you can find a non-trivial square root of n, then you can find a non-trivial factor of n. Why should there be non-trivial square roots of n? Let's just talk about the case where n is, because this is the case that's of interest for the RSA algorithm. But this discussion generalizes quite easily. But supposing n equals pq, then when is x squared congruent to 1? It's congruent to 1 if and only if x squared is congruent to 1 mod p and x squared is congruent to 1 mod q. Now how can that happen? Well, you need x to be plus or minus 1 mod p and plus or minus 1 mod q. And by the Chinese remainder theorem, all four of those possibilities can happen. You can have x being 1. So the trivial ones would be when x squared is 1 mod p and x squared is 1 mod q, and when x squared is 1 mod p and minus 1 mod p and minus 1 mod q. Those would be the two trivial square roots of 1 mod n. But the two non-trivial ones would be when x squared is minus 1 mod p and 1 mod q, or 1 mod p and minus 1 mod q. Let's just check that in when n is 15. We have 4, which was 1 mod 3 and minus 1 mod 5, and minus 4 is minus 1 mod 3 and 1 mod 5. So when n is a product of 2 primes, there are 4 non-trivial square roots of 1. 4 square roots of 1, of which 2 are non-trivial. So the next question is, how do you get hold of a non-trivial square root of 1? And I haven't got very much time. I'll just give a quick preview of it, but we'll do that a bit more next time. So the rough idea is you just pick any old w. Somehow, using some quantum magic, you find the order of w mod n So you find the smallest r such that w to the r is congruent to 1. If you're lucky, r is even. And if r is even, then we take w to the r over 2. That's going to be a square root of 1. Because we chose r to be the order, this won't be 1. It might be minus 1. But if you're lucky, it's not minus 1. And a little argument shows that the chances of being lucky will be at least 50% or something like that. So if you're unlucky and you find, oh, we've done all this quantum computation which took years to build and everything, and you just managed to find a square root minus 1, well, you just have to hope that it wasn't a sort of machine that destroys itself after one use or something. And then you keep on going, you pick random w's. So actually I should just make a general remark. With quantum computation, there is a probabilistic element to it. When you make a measurement, weird things could happen. You have to set it up so that with probability 3/4 or something like that, at the end of the day you'll get what you want. And then if you don't get what you want, you just run the experiment over and over again until you... And then if you run it enough times, then the chances that you won't manage to factorize your number n can be made as small as you like, very, very, very quickly. Okay, so I'll say more about how we're going to find. So, in a sense, I've boiled everything down to how do you find the order of a typical element in a multiplicative group mod n. And by the way, if you pick a random w, it might not be co-prime to n. But then you're extremely pleased because you could have them, so that's not a problem. Okay, we'll carry on next time.